little rough. Just a touch. Good morning, everyone. Oh, geez. Good morning, everyone. We will all take our seats now and get ready to do some science. My name is Lindsay Goodwin. I'm chairing this morning. I'm an assistant professor at the New Jersey Institute of Technology, but I'm also involved with the CSSC and DEI task force. So if you have any questions, comments, queries about things happening, come talk to me or other people on the CSSC. So our first speaker today is Dr. Varney. She has done phenomenal work within the community. And one of the things I was talking to her about just before turning on the mic and stuff like that is I was actually kind of shocked, surprised that like she had not already given like an early career highlight. I think like even though she's early career is overdue already. She's also a former CEDAR student rep. So like particular sort of like, I don't know, like cohort, I guess. But yeah, so I'm very excited to introduce and have Dr. Burley speaking with us this morning. So give it up for her.
Thank you for that wonderful introduction, Lindsay. I'm very happy to call CEDAR my science home. And thank everyone for the opportunity to talk to you today about modeling the high latitude ionospheric upflow and outflow. As Lindsay had mentioned, my name is Dr. Megan Burley. I'm a research scientist at the Naval Research Lab in Washington, D.C. So the high latitude ionosphere is such a dynamic and interesting environment. Thermospheric winds can arise from solar forcing, plasma convection, and waves. These neutral winds may interact with the ionospheric plasma through collisions, driving upflow or perpendicular motion. Other ion motion drivers, such as electric fields and auroral precipitation, may also be present and drive upflows. Ions may then undergo further acceleration from transverse heating by broadband ELF waves. And at high altitudes, the mirror force may propel the ions to escape velocities, resulting in outflow to the magnetosphere. One of my favorite ways to probe this dynamic environment is by sounding rocket. The scientific urge to explore this dynamic environment has been long-standing. For example, Torricelli carried a barometer up a mountain in the 1640s. In 1749, kites carrying thermometers were flown in Glasgow. And by 1893, huge box kites had taken instruments over 3 kilometers high. Unmanned instrument-carrying balloons had reached 16 kilometers by 1893. And Ruggieri had rocketed small animals into space as early as 1806. Don't worry, the payloads were recovered by parachute. And by 1830, Ruggieri's rockets were able to lift a full-grown sheep. So we're getting higher and higher and heavier payloads. In 1906, Alfred Ball had employed rockets to take cameras to higher altitudes. Ball's rocket carried an 8x10 photographic plate stabilized by a gyroscope. And in 1929, Robert Goddard placed a barometer and a thermometer on a rocket to measure ambient conditions. Unfortunately, it attained an altitude of only 52 meters. The middle figure here shows Dr. Goddard. He is the second person from the right, and his colleagues are holding a liquid-propelled rocket in 1932 at their New Mexico workshop. Another interesting piece of sounding rocket history is the raccoon. See the figure on the left. The basic idea is to lift a small sounding rocket high above the dense atmosphere with a large balloon. Once enough altitude is attained, the rocket is fired by radio signal straight up through the balloon, whoosh, and the rocket will reach much higher altitudes than it could from the ground. The raccoon has turned out to be a simple, cheap way of getting high altitude data without special facilities. Many raccoons were fired between 1952 and 1960, but once satellites and high-altitude sounding rockets became available in adequate numbers, the use of raccoons declined. But if you would like to know more about the early history of sounding rockets, I recommend this book, NASA Sounding Rockets from 1958 to 1968. It is freely available at the website here on the right-hand side of the slide. So modern sounding rockets come in all sorts of combinations of stages and lifting capabilities. Here are a few examples from the NASA Sounding Rocket Handbook. And depending upon the science targets and the weight of the instrument suite, different rockets are better suited. For example, the very tall rocket on the left figure of the right-hand side is approximately 70 feet tall, so that'd be about 12 of me stacked end to end. And imagine that stuff full of science. So another favorite method of mine to probe the ionosphere is via incoherent scatter radar. Different versions have different altitude ranges that they can probe, but they all provide data products of your electron density, your ion temperature, your electron temperature, and line of sight velocity. And while these may be some of my favorite ISRs, Sondrestrom unfortunately got defunded in 2018. Arecibo, located in Puerto Rico, suffered a catastrophic failure in 2020, and the Resolute Bay site experienced a fire last year. So science can be tough, but fortunately there's also a database called Madrigal. And so for the students out there who have not had a chance to delve into the depths of Madrigal, I highly recommend it. You'll be able to find decades upon decades of measurements from these instruments and others that are applicable to our scientific community. There's a lot of interesting data there to work with. So given that we have a long history of measurements and amazing capabilities to take modern measurements, as a modeler, I'm still asking the question though, why wait for an event to occur, hoping that instruments are turned on in the right location at the right time? What about the benefits of being able to fill in the blanks between data measurements to see what the ionospheric response is as a whole? Wouldn't it be nice to be able to deconstruct the ionosphere into the basic processes that are responsible for its current state? And how cool would it be to reproduce past ionospheric events, as well as predict the future? So then that really brings me into my passion, the power of using physics-based models for science. And yeah, there's a little asterisk up there that a model is only as good as its underlying rules and assumptions. So there are many different options for physics-based ionospheric models. For example, we have GIDM, the global ionosphere-thermosphere model, which is great for looking at the whole Earth. That is an image of GIDM's output over Alaska, our perpendicular ion velocities. We also have Gemini 3D. This is the Geospace environment model of ion neutral interactions, which is a local scale model designed to work at a much higher resolution. So for that same space and time, we have the Gemini 3D outputs overlaid over GIDM's outputs. And then as a third flavor of ionospheric models, we have Gemini-TIA. This is a 2.5D branch of Gemini that is well suited for the high latitudes. And so Gemini-TIA is based on a bi-Maxwellian distribution that incorporates ionospheric chemistry and transport needed to simulate ionospheric dynamics above 80 kilometers and includes the possible effects of low altitude wave particle interactions. As inputs into this model should then drive the ionospheric response, it can accept your neutral temperatures, densities, and velocities. And then also it can handle the input of DC electric fields, auroral precipitation, and ELF wave power. So overall, this allows us to provide a description of forcing of the ionosphere from above and below. With these variety of inputs, then Gemini will specify the ionospheric response and solve for 6 ion species and electrons, and provide the time evolution for each species of the density, velocity, parallel, and perpendicular temperature. And it can be set to a grid cell size as small as 100 meters or as large as tens of kilometers. And with the way that Gemini-TIA is structured, it is very well suited for ingesting sounding rocket and ISR campaign data for investigations into ionospheric dynamics. One of these investigations has been into the eisenglass sounding rocket campaign. So eisenglass launched in 2017 into a substorm expansion. This sounding rocket campaign contained both ground-based and in-situ rocket data that I have used to drive Gemini-TIA. And then this lets us examine the impact of different driver resolutions. The in-situ measurements from the rocket have a much higher resolution as compared to the ground-based measurements. So if we look on the left-hand side here, we have a time sequence of white light imagery. The rocket trajectory is overlaid in blue. The Pfizer flow measurements are the red arrows, and sequential in situ rocket data is the yellow arrows at a 5-second cadence. Apologies if it's a little bark for the people in the back. So the directionality of the plasma flow evolves as the rocket traverses the arc. So as we progress from the top to the middle to the bottom image on the left, we can see the yellow arrows are pointing towards the left, and then they point downwards in the middle image, and then they're pointing to the left again in the bottom image. Overall, there is general agreement between the rocket and the Pfizer data, so the yellow and the red arrows point in the same directions at the same time. In general, the ground data-driven simulations are capturing the general shape of upflow and contain both time and space variability, but at the loss of those fine-scale details. So for example, if we look at Pfizer data, this is going to be this top figure here. The original Pfizer data is pretty coarse as compared to the model grid resolution. Once we interpolate it onto the model domain, it becomes this smoother image up in the middle. And then if we just have a virtual rocket trajectory trace through that, we can then do a sanity check that the black dots are pretty co-located with the red line, which is the interpolated Pfizer, which is trending the same as the blue line, which is the in situ rocket measurements. And so overall, running these different simulations, we can then back compare the ion temperature outputs from the model to the in situ measurements from the FIPS. So that is the final figure down here, where all of the little polka dots are trending, the green lines are following, and then the black and the blue lines lose the fine scale details. How am I on time?
You got some minutes.
Okay, thank you.
No problem. I got you.
So overall, simulations driven by eisenglass's flow and precipitation data, so the in situ measurements, are able to reproduce the in situ ion temperature measurements better than the ground-based data. But the ground-based data contains the spatiotemporal variations, which you do not get with the point measurement moving of the rocket itself. So it becomes a trade-off in what are you trying to investigate. So auroral motions can also have a strong impact on the ionosphere. This is from a case study of the ReNew-2 sounding rocket, which was launched in 2015. On the upper left panel here, we have the all-sky imager measurements from that evening over the course of about an hour and 15 minutes, give or take, is what I've movied up here. The blue line is the trajectory trace of the ReNew-2 rocket. If through the imager's field of view, we trace out along that rocket what the brightness measurements are, we can build up a keogram. And so then that is the figure down on the bottom left. So within the keogram, there are some distinct periods where the aurora brightens and then moves poleward. And then this is our poleward moving auroral form. Poleward moving auroral forms are quasi-periodic sequences that have a repetition rate of about 2 to 15 minutes and are typically associated with pulse reconnection, the magnetopause. But they can be comprised of smaller subarc structures with spatial extents down to about 100 meters. And they may directly impact ionospheric plasma escape due to highly transient soft particle precipitation. So if we take the rocket measurements that have that high resolution and we replicate it across all the PMAPs, so we are extending beyond the limitations of just data during the rocket flight. And then we can modulate that by the brightness. We're able to do data-inspired modeling. So then that lets us have a longer simulation to explore the consequences of these realistic spatiotemporal drivers. So the soft precipitation elevates electron temperatures. So this is now, we're discussing the figure on the right. The bottom left portion of that is our electron temperature output from the model. We can see there are regions where it becomes much more bright and orange. This is where the soft precipitation has elevated the local electron temperatures. There is structuring now in the latitudinal extent. We have a north-south distance on our x-axis, and we are covering a span in altitude from about 80 kilometers up to 2,000. So the soft precipitation is elevating electron temperatures, which is enhancing the field line upflow from the plasma. And then this cumulatively drives more O+ to higher altitudes. So that shows the uplift of the O+ in the upper right panel here. And then the variable dwell time of the Pmass, because they're coming into the field and then they are leaving and moving through the simulation domain, coupled with the hysteresis of the 4+ Pmass we saw that night, can create altitude, latitude, and temporal dependence in the ion upflow. And then for my last 5 seconds, I just wanted to really then zoom back out, because these are studies that we have conducted within the local scale ionosphere, really digging into the dynamics driven therein. But we can also do this from a global perspective and see what the impacts of ionospheric dynamics are on the magnetosphere. So recently, GIDM has been two-way coupled to the rest of the space weather modeling framework. This allows to have physics-based conductance being passed out and impacting the MIT system. Movies are cool. See me if you want to see that. So in brief, the original way of doing it is that top panel, but by using the physics-based conductance from GIDM instead, on the bottom panel, we can see that we have different structures. The day side conductivity is no longer symmetric. And the magnetosphere on the left here has changed shape between the top and the bottom panels. And with that, sorry I am long, but thank you for your time.
Cool. We don't have a lot of time for questions, but I'm drunk with power. So if anyone has like a question that they'd like to ask. Yeah. Run, Andrew, run.
Hi, I'm Roger Varney from UCLA. In your second to last slide showing the Pedersen and Hall patterns, it looks like your physics-based Pedersen conductivity is dramatically lower than the older empirical models Pedersen conductivity. Do you have a physical understanding of why that's happening and which one is closer to reality?
I have leads, but no answers yet. But when I have answers, I will definitely get back to you.
Thanks.
Thank you so much. All right, Dr. Dr. Becker, you are next. Please report to the stage. Yeah, sorry. Okay. Oh, yes, I have to do stuff up here, don't I? I'm the best at sharing. Cool. Share screen. Okay. Yes. And bam. Needs to be there. Well, bam, there you go.
Okay.
Thank you.
Thank you very much. Good morning, everybody. And many thanks to Larissa, Li Ying, and all the other organizers for giving me the opportunity to talk about my work from the last couple of years about explicit simulation of gravity waves in a whole atmosphere model. So this is work together with a number of colleagues that you see here, and the list could go on, of course. I want to talk about why gravity wave resolving global simulations are important, or are an important tool for many science questions of the middle and upper atmosphere. I want to present you a few examples, and of course I will also talk about my personal views about the methodologies to be used. So let us first talk about the pros and cons of a conventional model setup where gravity waves are parameterized using the conventional framework. Of course, you are aware about the pros, that it's not very much computationally demanding, and that you, for example, can simulate a self-induced QBO. We also assume that the major dynamical features of the middle atmosphere, like the cold summer mesopause, are captured in such a model. But as you will see, the problems already start in the upper winter mesosphere. So, and the reason is that a conventional gravity wave scheme is usually based on two strong assumptions, namely the single column approximation and the steady state approximation. And the cons that result from that is you actually do not have continuous sources, but launch level parameters that are called sources. You have a spectrum of monochromatic waves that are there all the time at each grid point. Instead of wave packets, there is no finite vertical propagation time. There is no lateral propagation, and most important for the upper atmosphere, no secondary or higher order gravity waves, no gravity waves that are generated from the polar vortex. And the consequences are, for example, that you usually get the wrong direction of the mean zonal flow in the winter mesopause region in such a model. You almost get no gravity waves in the thermosphere, except for high frequency gravity waves from deep convection that are also dissipated by molecular viscosity, say below 200 kilometers. And also very important, I think the gravity wave tidal interaction is incomplete in a conventional model. So here's a result. Here are examples for the wrong zonal wind direction in the upper winter mesosphere. This is from a paper of Hindley et al. And this here is from Lin Harvey et al. You see here a comparison of radar measurements of the zonal wind over South Georgia. And here southern hemispheric winter. And you see the WACAM, for example, shows the wrong direction of the zonal wind. And this deficiency is summarized here in this plot from Lin Harvey. So in the southern hemisphere, you have this deficiency basically all the time. In the northern hemisphere, you have it mainly when the polar vortex is strong. So SSWs are fine for a model, but a strong polar vortex is bad. Why is that? And the answer was actually given by Qinchao Chu's LiDAR measurements over McMurdo a couple of years ago. And she calls these gravity waves here that she saw during wintertime all the time persistent gravity waves. And according to conventional wisdom, these waves shouldn't be there. So what is it? You also see that the vertical wavelength of the gravity waves in the southern winter hemisphere increases with increasing altitude. So these cannot be westward gravity waves. The zonal wind decreases with altitude. And therefore, if the vertical wavelength expands, these have to be eastward gravity waves. So why are there eastward gravity waves, and why are the eastward gravity waves even stronger when the polar vortex is stronger? And I will give you the answer in a second. We ran a high resolution general circulation model with resolved gravity waves, and we saw similar results for this typical behavior of these gravity waves in the southern hemisphere. And so the new model version that we use for these kind of investigations is called the high altitude mechanistic general circulation model, HIMCM. It's based on a spectral dynamical core with a high spatial resolution. It includes all kinds of ingredients that you need for a climate model, also a non-hydrostatic direction for the thermosphere, and a consistent expansion of the thermodynamics into the thermosphere. We call it mechanistic because of the simplified parameterizations for, say, radiation and moist convection, and there is no explicit chemistry, but we do have ion drag in the thermosphere, which is quite important, of course. And the model can be nudged to mirror 2 reanalysis, and we do this in spectral space. And this is quite important for the simulation of gravity waves. If you want to simulate gravity waves and you want to compare to observed events. What's special about the HIMCM is that the non-resolved scales are parameterized by a physics-based scheme for macroturbulent vertical and horizontal diffusion. So the idea is, if you want to have a gravity wave resolving model, A high spatial resolution is necessary, but by no means sufficient. What you need in addition, you need a parameterization of the non-resolved scales, because you always have the nonlinear interaction of the resolved waves, and you have a forward energy cascade that has to be balanced in one way or another. So this scheme that we apply consistently includes also molecular viscosity, and thereby the gravity waves are self-consistently dissipated in the upper thermosphere by molecular viscosity, and no artificial sponge layer is required. And we can also simulate the gravity waves, as I said, for observed events by using the nudging method. And the effective horizontal resolution is estimated to be about 200 kilometer wavelength horizontally. So as I said, the major assumption in such a model concept is that the unresolved gravity waves that you do not get with your limited spatial resolution are local. This means they represent a macroturbulent inertial range. This is just the assumption in order to build a consistent model. Of course, this assumption is not entirely true, but it becomes the better, the higher the spatial resolution is that you can afford. Here's a comparison of the resolved gravity waves when we compare to MERA2 reanalysis. So the model is nudged to MERA2 reanalysis, but not these scales that you see here. These scales develop freely in the high MCM, but as you see, the phases and the amplitudes of the larger scale portion of these gravity waves compares quantitatively well with MERA2. And of course, there are additional small scale stuff here that you can see. This is a comparison with air satellite data for the whole month of January 2016. And in order to compare here the temperature variance from the high MCM, we first had to apply the observational filter for the AIRS instrument. And then you see that you can capture the gravity wave hotspot over Europe, the gravity wave tiny hotspot here over Eastern Canada, and so forth. And you also may notice that the strongest gravity wave activity resides in the regime where the polar vortex has the highest wind speeds. This is now the zonal mean circulation from the model. And I know this figure is a little bit complicated. Left-hand side is for January, right-hand side is for July 2006, so this is 2020. And zonal wind temperature, EP flux divergence, residual circulation. And I will mention a few things here. So first of all, you may notice, so I indicated this here with these arrows, there's continuously eastward zonal wind in the winter mesopause region as is observed. So why is this? We see there's eastward EP flux divergence in these regions. And you see the eastward EP flux divergence is stronger in the southern hemisphere. This eastward EP flux divergence is, of course, due to all waves that are resolved here. So it includes all those tides and planetary waves. But when you look more into the details, this is mainly due to gravity waves. And these gravity waves are so-called secondary gravity waves that result from multi-step vertical coupling. And they are stronger in the southern hemisphere because the polar vortex is stronger. And as a result of that, you also see that this reversed residual circulation that you have in the mesopause region extends all the way to the winter pole in the southern hemisphere, but not so in the northern hemisphere. Yeah, so the summer-winter circulation here in the upper mesosphere is also affected by the resolved waves, but it's mainly driven by the zonal component of the ion drag, which goes up here to more than 1,000 meters per second per day. So this is how multi-step vertical coupling looks like in a snapshot. So this is for a time when the polar vortex was strong. And you see here the so this is a snapshot, longitude, altitude of the temperature perturbations from the resolved gravity waves. On the right-hand side, you have the large-scale zonal and meridional wind components. Here you have this hotspot over Europe, and from the orientation of the gravity wave phases, you can tell that these are primary westward propagating gravity waves. Presumably in this case here from the polar vortex, but then these westward propagating gravity waves dissipate here in the lower mesosphere, and then gravity waves propagate in all directions in the mesosphere, and these waves then dissipate here in the mesopause region. And as I said, because of the general decrease of the zonal wind with increasing altitude, you get prevailing eastward gravity waves that dissipate here in this region. And this accounts for the eastward gravity wave track. That is important again for the mean wind direction. And then from here it goes on and you get secondary and or tertiary and higher order gravity waves that have very large vertical wavelength and also very large horizontal phase speeds. And then 7.5 hours later, the picture looks about similar here in this regime, but as you have seen, because the mean winds have advanced to the west, also the gravity wave picture here looks entirely different. This is an average of how the picture of the gravity waves then looks like higher up in the thermosphere at around 300 kilometers. So this is what I call an average daily cycle for late December in 2016, again, a period when the polar vortex was strong. And typically during local time noon, you see the strongest gravity wave amplitudes. During local time noon, you see the strongest gravity wave amplitudes, and you see that this pattern goes around over the course of the day. And let's focus here on 12 UT over Europe. The arrows show the large scale wind, or the black arrows show the large scale wind that goes from the day side to the night side. And because of the auroral circulation, it's somewhat shifted here into the dawn sector. So you have a strong westward flow here in this regime. And the gravity waves amplitudes are on average maximum where you have the maximum wind speeds. And as you can see from the gravity wave momentum flux, which is given here by the white contours, the gravity waves propagate on average roughly against the mean winds at these altitudes. And these gravity wave momentum fluxes are about 2 orders of magnitude larger than the gravity wave momentum flux that you have beneath the summer mesopause, for example. So there should be a strong gravity wave tidal interaction that we have not analyzed yet. But this is how the picture looks like. And of course, this is entirely consistent with the equatorward propagation of quiet time TIDs that may be driven by those gravity waves. And this is shown here in this figure where we compare the gravity wave perturbation with DTEC. This is here for December 27. This was a time when we had quiet time conditions, and you see here in this latitude time section that you have the southward propagation of these gravity wave perturbations, and that the wave characteristics in terms of frequencies or phase speeds and wavelength increase very nicely with what you see in the DTEC. So we also looked during an SSW when the polar vortex was weak or even reversed. And this is still quiet time, January 13th, 2017. And then you see that the amplitudes are strongly reduced in the model, but also in the observations. So the whole vertical coupling from primary to secondary, tertiary gravity waves and so forth depends very significantly on the intensity or the strength and the stability of the polar vortex. When the polar vortex is weak or SSW, all the gravity waves are weak. This is the example of the Honga-Tonga simulation, where we try to simulate the higher or the multi-step vertical coupling that was initiated by this volcanic eruption 1.5 years ago. And here we have to do something different because the updrafts of the volcano, they were so large and they localized, you cannot resolve this in a global model. And what we did, we used the Sharon Vardas's Mesosphere model, which detects these updrafts and then does ray tracing simulation of the high frequency, very localized primary gravity waves. And then we compute the body forces from these primary gravity waves when they dissipate in the mesosphere or in the thermosphere. And you see these waves did not propagate very far from the regime of the Tonga, and they caused huge body forces, huge momentum deposition in the mesosphere and in the thermosphere. And these body forces were then plugged into the HIMCM, into the global model, and we simulated the response. And this is what you see here in terms of the vertical wind. It's a broad spectrum of gravity waves with the large horizontal wavelength propagating propagating also faster and arriving here over the America continent much earlier than the small scale stuff that comes later. We then coupled the model output from the HIMCM into the ionospheric model SEMI3 of Joe Huber. And Joe made a simulation with and without the Tonga eruption. So we had, of course, also simulated January 15th without the input from the Mesosphere model. And this is shown here on the left-hand side, the results. And the results with the Tonga eruption are shown on the right-hand side. In the upper panel, we have again the vertical wind from the model. And here you see in terms of the electron density that the electron density is really perturbed by these vertical wind phases. And you see a different evolution of the structure of the plasma bubbles here in the equatorial region over the West Pacific. And in fact, for the Tonga eruption, Joe found a huge plasma bubble activity. Yeah, okay, and this is published here in this paper by Joe from GRL this year. This is a comparison of the simulated zonal wind perturbations from the Mesosphere HIMCM with measurements from the from ICON, and these are here 4 orbits of the ICON, and you see here how the wave phases in the ICON measurements of how the wave phases from the Tonga secondary waves arrive. And the estimated phase speeds of these wave perturbations goes up to 700 meters per second in the thermosphere. And here is the corresponding simulation of the zonal wind perturbations from the HIMCM. And we tweaked this a little bit in terms of amplitude and timing so that the figure would look a little bit better given all the uncertainties. But nevertheless, you see that the HIMCM actually captures these observed wind perturbations. And these strong perturbations in the zonal wind, of course, cause a perturbation in the zonal electric field along the magnetic equator, and this has then corresponding effects for the plasma instability and the generation of plasma bubbles. This is here how the plasma bubbles looked like over the Atlantic region from the gold data from the emission of the atomic oxygen. And there was a regular EIA on January 14th before the eruption. The emission was a little bit stronger than usual because of geomagnetic storm activity. And we looked also on January 16th after the eruption, and the figure looked more or less the same. However, when we look at January 15, when the Tonga waves had gone through this region here, you see in gold that the crests of the EIA actually merge, and it somehow looks weird, completely different as usual. And something similar is also seen in the SEMI3 simulation. So we also did the SEMI3 simulation without the Tonga eruption, and then everything looks as usual, so to say. So that's why I didn't show it. So the SEMI3 actually captures some of the changes of the equatorial ionization anomaly that was induced by the Tonga eruption. So here's the same figure 45 minutes later. So my last example are tides, and there is an unexpected DE3 in the southern summer mesosphere. And this is a work together with Jens Oberheide. Here are, so how much time do I have? Oh, that's good. These here are kilograms from the HIMCM and MERA2 at 70 kilometers. And this is the average daily cycle in the model when we averaged the whole January from January 1st to January 20 in 2017. And you would expect a westward propagating diurnal, a migrating tide with zonal wave number 1. However, you observe an eastward propagating diurnal tide with wave number 3, the DE3. And this is not only seen here in the model, but also it's indicated very nicely in MERA2. You see it also in the model when you look at snapshots and then you look at the in longitude height sections at, what is this, 50 degrees south or something, or even 55. And you see here the eastward propagating DE3 tide in the mesosphere. And this is also indicated here in MERA2. And we looked also into the CEDAR data and made a new analysis of that. And it's also confirmed by CEDAR. So there is a DE3 in the middle to high latitude summer mesosphere in the southern hemisphere. And this result is summarized here in these figures, where you can see the tidal amplitudes of the different components, DW1, SW2, and here all eastward, non-migrating eastward tidal components, and the DE3 with white contours. And you see that this additional maximum here that looks like an appendix is actually captured almost by the DE3. And it's quite strong. It goes up to 6, 7, 8 Kelvin. And this is also indicated here from the MERA2 analysis. And there is an older paper of my former boss, Franz Josef Lübken, when they did temperature measurements with the resonance LiDAR at the station of Davis at Antarctica. So this is a paper from 2011, and they found the strong diurnal diurnal tide in the upper mesosphere. So it extends up to about 90 kilometers. So this here is a time interval of 48 hours to better show how the tide looks like. And so you have the strong diurnal tide here with an amplitude of 6 to 8 Kelvin, which corresponds very nicely here to the DE3. So the question is, what is it? We haven't analyzed it yet, but I assume since such a result is not found, or I haven't seen it at least, in a conventional model with parametrized gravity waves. And since the gravity wave tidal interaction is incomplete in a conventional model, I assume this is also a topic that you need to address with a gravity wave resolving model. So here's my summary. So I think the main message from all this is, for a gravity wave resolving model, you not only need a high spatial resolution, but also a physics-based macroturbulent diffusion scheme. And this is also where the future goes, is heading for higher resolutions and improving such schemes. Thank you very much.
Thank you very much. We are running behind on time, but is there a quick question from the audience? Oh, yes. I'm going to switch over the slides while we do that.
This is Xinzhao Chu from CU Boulder. Eric, thanks for this very nice work and talk. Just a quick question. You know, for that Tanga volcano eruption, I'm wondering if there's any non-hydrostatic stuff and how your high MCM model handles this non-hydrostatic process.
So these waves from Tonga certainly also require non-hydrostatic dynamics to some extent, but you can also simulate non-hydrostatic waves with a hydrostatic model. The only thing you're doing wrong is you're getting too large phase speeds, too high amplitudes of the too high frequencies, and too large amplitudes of the vertical wind. So which means when you apply this hydrostatic, non-hydrostatic correction, you get more realistic results.
Thank you very much. Up next, we have another early career science highlight from Dr. Deshpande. Just another note, this is also a very overdue talk because we were supposed to have her last year, but it didn't quite work out. So it's very exciting to have you here. And time's yours. Here's the mic.
Awesome. Good morning, everyone. Namaste. I'm Kshitija Deshpande from Embry-Riddle, Aeronautical University in Florida. Thank you to the CEDAR committee for accommodating me this year. I was not able to make it last year. So I will be talking about GNSS remote sensing of the ionosphere with machine learning and modeling. So I just would like to thank my co-authors, Matt Zettergren, Leslie LaMarche, and many others, and my PhD students, Murray and Pralay, and 2 undergrad students, Kristen and Nick, who are not at Embry-Riddle anymore. They are graduated. They are in Boeing and Google respectively, but they're helping me finish their work as a paper still. They're just interested in all this. I would also like to thank NSF NASA and for funding this work. Thanks to Chain Group for providing us data. And I would like to thank all my collaborators whose names are not here, my students, and more than anything, I would like to thank this community, the veterans in this, all the research that you have done. I'm standing on the shoulders of the giants. So thank you so much. Let me begin. This is a mandatory slide about scintillations. So, okay. Okay, perfect. So ionosphere has cloud-like structures called irregularities. Whenever the radio signal passes through them, we experience fluctuations in the signal. That's basically a nuisance in PNT solutions, position, navigation, timing, but we use it for remote sensing. That brings me to my next slide, which is, if you want to call it, high-level story of scintillation or history of scintillations, whatever it is. Well, so these errors are great for science. We use it for remote sensing again, because we have abundant data available across the globe. Now, since 1970s, people have been studying irregularities, which are dynamic electron density structures. They use it for multi-scale analysis, and especially to understand the cascading of energy, which we are again exploring. There are lots and lots of case studies, climatological studies, statistical studies of high and low latitude simulations. We are also using propagation model, which is coupled with an ionospheric model and more auxiliary data, which is bringing all bringing new information. I'll talk about it in a minute. Before I go ahead, for high latitudes, these are typical sources of irregularities. In cusp, we have Kelvin-Helmholtz instability, which is shear. In polar cap, we have GDI, which basically are the reason for the polar cap patches. In auroral oval, we have auroral precipitation. That brings us to some of the science questions we're trying to understand. So first is, can we categorize these irregularities based on their scintillation signatures, temporal and spectral? And then the second one is, what is the relationship between scintillations and the irregularities that produce them? So where is machine learning coming in? A typical science grade GPS receiver, GNSS receiver, collects high rate 50 hertz phase and amplitude data for 35 satellites at one time in the sky. So by definition, a big data is high volume, high velocity, high information, variety of information data, and that qualifies GNSS data to be big data. Whenever we are working with big data, it is efficient and more convenient to explore machine learning algorithms, and that's where machine learning is coming in. These fields, machine learning and deep learning, are growing fields, like they are fast growing fields, but we need to be careful how we use them. They are not to be used as black boxes. For those who have worked with machine learning would appreciate that data pre-processing is the most crucial step before you even apply any kind of machine learning algorithm. So my current quest, that's right now what we are looking at, which is, can we categorize high latitude scintillations based on their source regions, which is polar cap versus auroral oval. Okay, so this is a paper that I am helping Chintan and Nick finish up. It's on their work where they categorized source regions with a machine learning model and a deep learning or neural network model. We use 2 years of data, chain data from 3 stations, which is 1 terabyte per year per station. And this is just to start with to build up our model. For labeling, we use SUSY-derived auroral oval boundaries. We used an unsupervised algorithm, which is called isolation forest. I'm not going to get into the detail in the interest of time, but just to give you an idea, the top 2 figures are an example of how it is able to detect scintillations, which are the fluctuations in the background noise. So that's the isolation forest we are using. And then we train a neural network model to categorize or classify scintillation events. We've so far achieved pretty good accuracy. What we figured out is neural network models are able to extract patterns, which is proving that the model is capable of distinguishing between auroral oval and polar cap events. This is a paper Murray wrote last year. It's creating database of high latitude scintillation signatures. So she is approaching the same problem with a different route. And this is where she's got hierarchical clustering, which is a kind of unsupervised algorithm. It deals with clustering data based on scintillation signatures. So just to give you an example, on the left, there's a phase time series for a bunch of time series, and you cannot distinguish any kind of a group, but this model was able to extract a group which has similar signatures. The phase PhDs, power spectral densities associated with those grouped signals is also shown. And the cluster, hierarchical cluster, which shows that group, I don't know if you're not able to see right here, this is a branch that actually tells, okay, all these signals belong to the same group or category. She's using the same approach and expanding it with decision trees. So that's where she is using decision trees to classify the events, specifically in the two regions. She's again using SUSY data, but not predefined boundaries or auroral oval boundaries. She's using the actual data. Hierarchical clustering to identify signatures that look similar, and then she does decision trees which have like tree-like structure. And all you do is all the machine learning algorithm does is finds these decision boundaries over these different branches and tries to find the shortest path to a decision where it says, okay, classifies an event to be a polar cap or auroral oval. What she's found out is whenever there's storm or something, the auroral boundaries expand so much that your polar cap and the auroral oval station come inside the auroral oval. So that screws up the labeling part. And that's why the algorithm cannot produce what it's supposed to produce reliably. So what about modeling? While we are exploring the machine learning categorization, we're separately looking at individual modeling studies. So for that, we're using two models, Sigma, which is a propagation model to generate scintillations on ground, and Gemini, which is an ionospheric model, which generates instabilities, which we put in Sigma and look at what would be the observed signatures on ground from different instabilities. So this is an overview. In the interest of time, I'm trying to put everything in a couple of slides just to give you an idea of what we've worked on and what we are working on. So we looked at gradient drift instability, which is in polar cap region. Those two pictures that you can see, one of them is the actual number density, and the second one is what we get from Sigma model, which is sort of an impression of what the signal would look like in a 2-dimension. This is not observed. You cannot get this from observations. What we found is GDI in its trailing edge causes scintillations. Leslie Lamarche led us into a multi-frequency study of again, polar cap, GDI stuff. And what we found out was you could see UHF and VHF scintillations, both with observations, and we could reproduce from modeling. But in order to see GPS signatures, GPS turbulent cascade was supposed to develop even further. So just to give you an idea, all these different frequencies are experiencing scintillation from structures that are different sizes. So GPS is much smaller, higher frequency, smaller wavelengths, so smaller structures. We've looked at Kelvin-Helmholtz instability in cusp region with Andres, and what we found out is there are oscillations associated with small scale structures in the vortices of KHI. Pralay Baggu, my PhD student, has looked at auroral oval and precipitation related study where he didn't use a Gemini sigma combination, but he used sigma with an inverse method or inverse modeling approach. He found out that E and F region irregularities have distinctive morphological features in spectral and spatial domain. He is now looking at the precipitation with respect to Gemini. So it's generating an auroral arc in Gemini and passing it through sigma to see whether we see scintillation. So go see his poster this afternoon. Okay, how am I doing on time? Excellent. So just to summarize, we are exploring different machine learning approaches to categorize these events based on source regions. We've looked at hierarchical clustering, decision tree, isolation forest, neural network, deep learning algorithms to detect, classify, and categorize scintillations. We are now exploring SVM, which is another supervised machine learning model, and go see Marie Val's poster this afternoon if you want to know more about it. We've investigated Kelvin-Helmholtz instabilities, GDI, gradient drift instabilities, in terms of modeling and scintillations. Looked at multi-frequency studies, again, in the GDI regime. Now we are looking at auroral precipitation, and hopefully we might be able to expand it to understand whether the secondary instabilities are of any importance to generate the scintillations. And we are also trying to look at spectral slopes of these different instabilities with this, compared to those slopes on the ground of scintillations. Finally, at least my ultimate goal is to have a combination of machine learning algorithms and modeling for scintillation prediction problems. Now, did we experience any challenges, problems? Yeah, a lot. So what is the most suitable machine learning algorithm? How can we be sure that the scintillation signatures are in fact distinct, which is our hypothesis? Then how can we create trustworthy samples to train a machine learning algorithm, which is really a headache. Now, in terms of modeling, is there just one type of instability that's causing scintillations or a mix of instabilities? Do we use refractive scintillations, diffractive scintillations, or a combination of both? What size of scale structures are we talking about with respect to scintillations? And finally, different primary and secondary mechanisms and their importance in generating the scintillations. There are many more. Actually, I would recommend you to look at our section in this book where we dedicate the whole section on the challenges. And I will leave you with this quote by one of the greatest thinkers of our time, Swami Vivekananda. When you don't come across any problems, you can be sure you're traveling wrong path. So I feel like I'm on the right path. Thank you for listening.
Do we have any quick questions? Oh, there. Oh, two over there. Okay, excellent.
Most interesting talk. My question is, do you plan to make this data set of categorized scintillation available, say, as an accompaniment to one of your papers?
So yeah, we will make it available after the paper is done. And this is just for 3 stations, but we would like to expand it for as many stations as we can. This is all freely available data from the chain website that we are using. And we will make the codes available. So even if you want to expand it for other stations, you can just grab those with the codes. So that's the plan for this paper. Thank you.
Thank you very much. Let me pull up the next slide. I guess kind of like a quick intro for this. So one of the things that the CSSC is trying to do is to have more international collaborations. So that's why earlier this week we talked about IceCat, but now we're going to hear about the Meridional project from Dr. Blanc. If you want to come up here. And sorry, I butchered your name right there. My voice is a little rough. Just a touch. Oh, we got your version 3. So excellent. No, not that. Let me get it going. It's going to give us all these warnings. And then, yeah, to process it, it would just be that. Okay, cool. You're good to go. Thank you. And the timer's down there.
Thank you very much. It's a great pleasure for me to address this audience. I would like to thank Larissa and all the organizers for giving me this opportunity to talk to you about this what I think is a beautiful international collaboration project. It's called the International Meridian Circles Program. I'm going to explain to you what is the concept in just a moment. We believe it's a major opportunity for science, space weather monitoring, and international collaboration. And I am speaking on behalf of the IMCP international team. So I am from the IRAP in Toulouse, France, and when I visit China, I am also a visiting professor at the Chinese Academy of Sciences. So let me tell you first about the bibliography. If you are interested in the project, I recommend these few papers. There is one paper by Shi Wang and collaborators about the Chinese Meridian project, which is the Chinese component of this big organization. And then the International Meridian Circle project, we have produced actually 3 papers. One is a report from an EC Beijing forum that was held in 2019, just before the pandemic. So just have a look and you will see better probably what is the concept. So speaking of the concept, I'm going to go through the idea that what we want to do is to start from science objectives, and from the science objectives to build an observation system that will address the science objectives. So the idea is that the lower thermosphere and ionosphere, LTI, or in our project, we call it the ionosphere and middle upper atmosphere, IMUA. It is the boundary layer separating plasma Earth above the lower ionosphere from fluid Earth, which is below. Well, this community knows that very well. So the region of the atmosphere of the Earth between about 90 and 200 kilometers, to make it simple, is the region where there is a maximum deposition of energy coming from above and from below. Vertical heat conduction in the thermosphere temperature gradients conducts heat to that region. A photon, particle, and Joule heating are also deposited mainly in this region. So to speak about what comes from above and speaking about what comes from below, atmospheric waves, and we've seen a lot of examples of studies of atmospheric waves propagating upwards in this meeting. We see how it's important, are coming from below and sometimes breaking or they're absorbed in this layer. So the LTI or LIT, it's a live TV screen, if you want, where we can detect disturbances propagating from above and from below. So in that sense, it's a fantastic tool to study natural anthropic hazards. So the main overarching goal of this IMCP project is written here: to build a global screen all around the Earth on which to detect, study, and monitor the images produced by the different natural and anthropic disturbances on this screen that you see in the middle of this panel here. So what kind of effects can we see? So to the right, you see the effect of geomagnetic field variations. That's the first thing. So at the decadal scale, the geomagnetic field is changing, and with it, all the features that we are studying are moving. Then space weather. So all the solar and interplanetary space activities indeed propagate through the solar wind, magnetosphere, and so on, and put their imprints on the ionosphere, as we know well. The global electric circuit is also connecting from the ground to the ionosphere. The global electric circuit, the electrostatic discharges during the thunderstorms, and so on. Atmospheric waves propagating from below and breaking into the upper atmosphere. Seismic activity, We don't know exactly what are the processes, but it's something to be studied. And finally, the effect of greenhouse gases, which means basically climate change in the upper atmosphere. So that's what we want to study. And the next figure shows here some of the top level subjects for study by the IMCP. Coupling to the sun and to interplanetary space, we would study the key energy transfer processes, entry, storage, deposition region. And we know there is a lot of deposition regions in the ionosphere and thermosphere. Coupling to the dense atmosphere, so atmospheric wave propagation from below, coupling to the global atmospheric circuit, and climate change in the upper atmosphere. And finally, coupling to solid Earth. So we want to characterize the effect of geomagnetic field changes on the long scale, some multi-decadal scale. That means we have to have an observatory which we have this duration. Effects of earthquakes on the upper atmosphere, that's another subject. And finally, it was illustrated briefly during this meeting, effects of volcanic activity. So from that, the idea is to try to design the optimal observing system. So we cannot cover the whole globe. And the idea is to try to choose 2 great circles in quadrature that will go through the best possible places to monitor from the ground with ground observations, the different types of disturbances I just alluded before. On these 4 Mercator maps, you see to the upper left that one of the 2 circles, the 120 degree east, 60 degrees west meridian, which goes through Asia and the Americas, actually goes through the geographic and geomagnetic poles so that it can capture both geomagnetic and geographic latitude variations in the phenomena. To the upper right, you have a map of the surface wind in the atmosphere. And it shows essentially that there is a big contrast between the ocean hemisphere, I mean the Pacific, and the land hemispheres. So we need to capture that also. And for that, we need a second meridian, 30 degrees east, 150 west, that will go through the central Pacific, and on the other side, through Africa and Europe. Lower left corner, we see that the maximum in lightning activity over the globe is in Central Africa, and that will be captured by one of the great circles, and in South America, and that will be captured by the other one. And finally, you see that the circum-Pacific fire belt is reasonably well monitored by the main circle, the 130 degrees, 60 degrees west meridian. So with that, let me show you exactly what will be the, or should be the deployment of these 2 great circles. So in brown, you have what we call the first meridian circle, Asia, Australia, Americas. And in green, the second meridian circle, Europe, Africa, and the Central Pacific. You see that through the Pacific, this chain goes through Alaska, to Hawaii, and to French Polynesia, which is one of the reasons why in my country we are interested in this project. A good example of deployment of local participation to this project is the Chinese Meridian project. You see here on this map of China, our Chinese colleagues have designed and actually deployed in 2 phases a set of instruments that monitor solar activity, interplanetary space, and ionospheric disturbances with both small instruments, network instruments, and large instruments, including 2 infrared scatter radars. So what are the virtues of the 2 circles? So the first meridian circle can capture, thanks to the Earth's rotation, all local times in 12 hours of UT. It also fully covers magnetic and geographic latitudes. It maximizes continental coverage, so which makes it easier, of course, for a chain that will be deployed at the surface of the Earth. And finally, it gives a good coverage of the circum-Pacific fire belt to study and monitor earthquake effects. We go to the second great meridian, this one. So here, in addition to the first one, Now you have two great circles in quadrature so that you can cover all local times in 6 hours of UT. This one will capture land-ocean contrast between basically Africa and the Pacific in climate and weather, so that's very important. It will go through the maximum region of thunderstorm activity in Africa. It will offer the longest continental traverse of the equatorial electrojet, that's in Africa. And finally, it will give a specific coverage of the ocean hemisphere of the Earth. So that's the whole idea of what we want to deploy. The project is just starting, especially in Europe and Africa. And I wanted to mention that there should be a focus on the unique potential of Africa as a place to deploy space weather programs and instruments. In Africa right now, there are both network instruments like magnetometers you see at the center, or GNSS receivers. You see the global map of Africa with GNSS networks which are deployed by different countries. And at the top, the GNSS network of Algeria. To the right, you have, let's say, more costly instruments, like in Morocco at the Oukameden Observatory. There is a Fabry-Perot interferometer, which was co-funded by an American institution and which monitors winds in the upper atmosphere. Now in Nigeria has managed to fund a Superdan type radar that will monitor with HF monitoring the drifts east-west and vertical in the region of the electrojet and the equatorial anomaly. And I think it will be a fantastic tool for equatorial aeronomy studies. So what is the concept of the observation system? This is to show that there is room for everyone. To the left, you see there are on-site instruments. This is a ground-based network. So you can have large facilities like IS radars, LiDARs, radioheliographs. You can have medium-scale facilities like HF radars, the sound, Fabry-Perot spectrometers, air glow imagers, and so on. And you can have more simple network instruments, basic ones like ionosondes, magnetometer, GNSS stations. They can be assembled in networks at the regional scale, at the latitudinal scale, along the latitude, along the longitude to make a longitude monitoring, or worldwide. Everything has a place. And let's say the logics and philosophy of this project is each instrument, ground-based instrument, bring a piece of the puzzle of the upper atmosphere forcing from above and from below, which is what we want to monitor. Each contribution is welcome, of course. A more effective monitoring of natural hazards achieved through data sharing and collaborative research is the overall objective of the project. So this is a collaboration between all nations, international, that will be benefit, we think, to all nations. In terms of project logics, let me say that we can do simple and we can do progressively more complex. To the left, the project can start with simple case-to-case collaborations between teams on monitoring disturbances of the upper atmosphere through exchange of data. Then you can develop data repositories to facilitate the exchange of data. That can be several ones speaking to each other and so on. At the center, it's sort of the dream of the project to develop collaborating research tools that could be something like an advanced study institute that will propose to the community shared online tools to work on data and address users' community scientific questions. So questions would be addressed by the community. Teams would be formed to work together from different countries. And of course, the data from the IMCP would be complemented by data from other ground-based and space instruments, by theory modeling available online, and also by artificial intelligence tools. With this, we build a virtual circle of knowledge building. The community asks questions, does collaborating research, answers questions, and then new questions are produced by the advance of knowledge. in the end, the scientific and societal benefits are there. New scientific insight, new monitoring capabilities, and new forecasting methods. Now you will probably ask me, what are the tools or the frameworks to do international collaboration? Well, it's of course a very important question these days. We have to see in which framework we can talk to each other among countries and do it for the benefit of science. So our idea is that the international collaboration on the IMCP project could be and should be under the umbrella of the International Space Weather Initiative, which is a program of the United Nations Office for Outer Space Affairs, UNOOSA. I was actually, well, this morning at 3 a.m., to tell you the truth, talking in Vienna to present something similar, because they have a workshop, an Eastward workshop, exactly at the same time as CEDAR. So we believe that Eastward is really the appropriate vehicle to discuss this project. All countries are there, as you can see. That covers very well the two Great Meridian Circles, and everybody has a place there. And to conclude my presentation, let me give you a few ideas about CEDAR community collaboration with IMCP. Of course, given the importance of the US community in space weather, contribution from CEDAR and participation of the CEDAR community to this project will be a game changer. The CEDAR community has the ideal expertise to contribute to the two great circles. Of course, one of the circles runs through the two Americas, the other ones through the Europe and Africa, so that this project will offer collaboration with African countries, and there are already many collaborations with African countries from American institutes. And we are looking for solicitation of European Union funding schemes to really collaborate between Europe, Africa, and the other big spacefaring countries in the world. There are several international meetings where this project will be discussed. So as I mentioned, in Vienna, actually right now, I've presented the IMCP this night. In Beijing, there will be an IMCP forum and summer school in September, where at least China and first Meridian component of the project will be discussed. We organize in my lab in Toulouse on November 20 to 24 of this year, the European Space Weather Week, where there will be a lot of discussions about space weather. And that will be a place, of course, to engage with the European space weather community. So I hope many of you will be able to come. We will be delighted, of course, to host you in wonderful Toulouse, more or less at the time of the World Rugby Games. So let's hope for the best. And we anticipate to kick off the build up of the Europe-Africa-Pacific Circle, a workshop sometime in the middle of 2024, likely in Africa, because it is very important to engage with African countries. And Nigeria has already expressed its interest to host such a meeting. So thank you very much for your attention, and I really look forward to discussion with all of you.
Do we have time for a quick question? Or do we have time? Do we have a quick question? Here we go. I saw Mears do the, oh, we have one in the back. Christina Lynch. Andrew. Yeah, there we go.
Hi, thank you for this nice presentation. I'm Christina Lynch at Dartmouth College. I was wondering if you could spend a minute talking about what, maybe you haven't got there yet, but have you started thinking about platforms for data sharing of combined and aggregated data products?
Well, in fact, well, maybe I will not go into the details, of course, for the sake of time, but in my lab in particular, we have an expertise on that, which is the Space Physics Data Center. We actually offer access to space data in that case from more or less all space missions about the Earth and planets. So we have an experience. In China, I think the core of the project will be also a data center. Actually, the Chinese Meridian project data are already available freely online. And I think there are many, or at least several places in the world which offer this kind of expertise for building, let's say, collaboration tools where you have access to data, to models, and where you can work with the two of them. So we really anticipate and look forward to collaborations on building this kind of tool. We believe this will be the core of our contribution, at least in France.
Thank you very much. Up next, we're going to hear about the EASY mission from Dr. Yi.
Thank you. Is it on?
Should be. Yeah, your timer's down there.
Okay, thank you. Well, let me first start by thanking the CEDAR steering committee to give me a chance to come over here to talk to you about a new mission called NASA's new mission called EASY. Last CEDAR, I was here, I gave a poster. And this time I really appreciate I have the opportunity to give you a little bit more details about the mission. And yesterday you heard sort of one slide overview about EASY. John McCormick gave the talk and the NASA things in there. And in this talk, I would like to focus a little bit more on how we actually make this mission happen. What techniques we actually use to give the data product to the community, especially the data product to the GEM community, as well as the CEDAR community. So, and of course, I always would like to start my team. We have an excellent science team, and many of the co-Is are actually present here. And also, I would like to thank the engineering team. So what does EASY stand for? EASY stands for Electrojet Z-mount Imaging Explorer. So by looking at the name, you probably already guess what the focus of the mission is and what technique we use. So EASY is a NASA mission to study it in mesoscale, so smaller scale, probably a few hundred kilometers, 100 to 500 kilometer scale of the electrojets is structure, spatial structure, and temporal evolution. So it's a cost-effective 6U CubeSat mission flying in pearls on a string configurations. The use of a very compact miniaturized radiometer to look down to measure the magnetic signature of the coupling between the magnetosphere, ionosphere, also how the neutral wind drive the formation of the equatorial electrojets. And this current system flows about 100 to about 130, 140 kilometers. So EASY studies the electrical currents, like I said, in the Earth ionosphere fundamental to energy transfer within the Sun-Earth system. If you focus on the auroral electrojets, the energy coming from the sun or from the solar wind stored in the magnetosphere, and for example, through substorms, will suddenly release those energy through the field line current system going down to the ionosphere, and then closes in the ionosphere. The Peterson current system, region 1, region 2 current, Peterson current system drive to give rise to the dew heating to the ionosphere. And the whole current system flying the other direction actually is the one that very intense. That's the one that we are going to focus on. So we're going to measure the electrojet in high latitude. And then also there's another one called equatorial electrojet. We also heard about that. We're going to spend some time looking at the structure of the aurora equatorial electrojets as well. So all the things that we have learned about field line currents, and all the auroral electrojets and equatorial electrojets are taken either from the ground magnetometer perturbation measurements or from space using magnetometers on board. And all those sensors using the fundamental techniques measure the magnetic field perturbation induced by the currents. But those measurements are all away from the currents, certain distances apart. For the ground, it's about 100-something kilometers away. From space, few hundred kilometers away. So the horizontal resolution of the measurements of the current structure is large because it's so distance apart. So we focus on a new frontier of this kind of measurements, the study of the smaller scales variations of the electrojet. So because of the ability, I'm going to talk about a little bit more, ability to measure smaller scales. So we're going to focus on two main objectives. But of course, there are a lot of measurements we can also obtain for, we can study. But first one, we want to resolve a 50-year-old hot debates about the structure of the high latitude current system. Modeling have been developed over the years, how the currents is, the field line current come down, how it closes in the ionosphere, and what the structure like. It could be hypothesis of a single sort of a loop system, or crossover two loop system, or actually two individual loop system as shown in here. All this require high resolution measurement near the midnight sector. And also there's newly developed theory about what just the general aurora electric jet structures. Control 8. Okay. But anyway, let me go back. Yeah, whether it's actually a single loop or actual form of lots of we call it widgets. Okay, so now all this, if we have a smaller scale measurement, we can really sort of point more better direction into the future research. So our mission implementation approach mainly by trying to do three things: taking advantage of the technology developed in the satellite technology, instrument technology, and a new technique. So we measured this electric jet spatial resolution by using, like I said, small compact instrument, but full view on a single spacecraft. Very compact, 5-centimeter aperture, radiometer, just flying on the satellite cross track. So basically, we can make the measurements of the current of magnetic fields in four tracks, separated by a few hundred kilometers, depending on different angles. And the second one we fly 3 satellites in sequence. And the separation of time, we use differential drag, basically to change the satellite orientation to either speed up the spacecraft as it drops in altitude, or just adjust the distance so we can see the same scene, how it actually evolve in 2 to 20 minutes. The third thing is whether we focus on sun-sync orbit, so midnight sector, so where the interest regions occur. So, but everything I talk about here, satellite technologies, 6U reasonably mature, and the sensor technology also have been developed by Earth Sciences. Instrumentation, drag has been used by the Signal missions, but one thing very, very unique, very, very innovative, make it possible is the Zeeman technique. So I want to spend a few minutes talking about that. So we use the Zeeman effect on the O2, V equal to 0, thermal emission, J equal to 1 to J equal to 0 transition, to 118 gigahertz emission line to obtain the current-induced magnetic field. What it says about Zeeman is the one in the absence of magnetic field, single line, J equal to 0, J equal to 1. But in the presence of magnetic fields, such as Earth's geomagnetic fields, plus current-induced magnetic field, then suddenly the line split, just to shown figure here. And this is the line observation provided by Aura MLS instrument. You can see the line actually split. And according to the Zeeman theory is well known, because he won the Nobel Prize for that, the distance between the two split lines proportional to the total magnetic fields of the environment. So if we can measure the distance between the two, the split amount, we know the total magnetic field. So this is very simple concept, but applied to many studies, or for the solar physics studies already. And that MLS provided data because they use this to measure the atmospheric temperature profiles. Right? So then if you look at the measurement, indeed, the line split, resolvable, one can make the measurement. So we actually carried out some studies, just derived it using the two separation, get a total magnetic field. The one on the left, just 1 year of the data, just collected and map it out. Immediately we see this is the Earth magnetic field signature. Shown on the right is IGIF prediction. So you already see that. Now we can use that to get the total magnetic field. But the one we are going after is the details. Earth magnetic field is 25,000 nanotesla to 65,000 nanotesla, but we are looking for a few hundred nanotesla to 1,000 nanotesla. So we want to see the noise. So we actually try to demonstrate that technique. If we make the measurement, after we make the measurements, subtract the background magnetic fields from the IGIF, which is geomagnetic field background model prediction, we can do a statistical study. The one shown on the left is the one that we're able to map out in the polar regions throughout about, I think, about 12 to 14 years of MLS data. And you can see that the structure of the perturbation for certain aurora index, for A index within the 400 nanotesla, that the feature just popped out. Indeed, it's very consistent in terms of delta B, how it varies, and then on the midnight sector, post-midnight sector, strong westward, and in the week post-noon eastward propagation electric jet just arises. It's very consistent with sort of statistical study knowledge about the electric jet. So the technology is there, techniques viable. So how do we actually make the measurement? This is an MLS measurement, limb measurement, full horizontal resolution. So the first thing we want to do is there any way we can get higher spatial resolution? The second one is this is only the total magnetic fields. Everybody asking, what's the value of that? We really want to get magnetic field vector. We really want to get a vector out. So the other property we really want to get after is the vector. So luckily we do know what these splitting spectra look like. This one is another very important characteristics of the Zeeman effect. The lines are polarized. So if we can measure the polarization of those two lines, because it's shown on the left, if looking perpendicular to the magnetic field line or looking to the magnetic field line or perpendicular to the magnetic field lines are different. So looking parallel to the magnetic field line, such as high latitude, you look straight down, very close to parallel, and the line, if it's exactly 90 degrees, it's completely circularly polarized. And for a certain direction, only one left hand, certain right hand. So then there's two lines, the pi line and shifted line disappear. Perpendicular one, all the intensity changes just differently as shown on the left. So actually we're seeing a flooded orbit, it's a mixture of the two. And then the data also demonstrate by the MLS data. So we're going to take advantage of the polarization state of the intensity of the line distribution, also intensity distribution. So if we measure all four stokes, we can get a total magnetic field as well as the vector of the magnetic field. The next one, we also point, instead of looking at a limb, we point straight down. The MLS has a 1.6 meter antenna size, huge, try to get because diffraction limited in order to get limb spatial resolution. If you look down, we can really miniaturize the instrument. So right now we are flying 5 centimeter aperture radiometer, 4 radiometers, looking straight down. And then once you're looking straight down, then you look at contribution, water magnetic field perturbation, most sensitive to our measurement, either the strength of the line or the polarization state, the one shown on the left. So we're actually capable of measuring magnetic field perturbation at an altitude around peak around 80 kilometers, which is great because that's 80 kilometers, but 25 kilometers, 30 kilometers below the current. Below the current has not only smaller spatial resolution, it's kind of higher spatial resolution. It's a lot better. So second thing, the magnetic perturbation also stronger for the same strength of the currents. So suddenly we are looking at something very close to the current system, the flying altitude, also a lot strong magnetic field perturbation. So we fly 4 sensors, flying this way, looking straight down, miniaturize the instrument, miniaturize the antenna, we can get magnetic field perturbation and induced by the current system and derive the current system. So I also would like to say about one thing about it, I call a secondary product. So if you look at the one on the left, it's the calculation of the one beam, we look straight down. The line, of course, become absorption feature. And this is just very much like the traditional microwave sensor making measurement of the temperature of the lower atmosphere. So each spectral region around the line are saturated, that means optically thick. So we are actually, each part of the spectrum provides you with an excellent temperature sensor. So you're looking on the right, you look at contribution of the signal coming from. So at the wings of the line, it comes from about 40 to 45 kilometers. And this temperature is shown on the left. So basically you measure the temperature at the wings. As you go to the largest absorption region, actually come and move up the altitude. So contribution function is telling us that we can measure the temperature from 45 kilometers, 40 kilometers, all the way to about 80, 85 kilometers. Give you a temperature profile measurement, just like the traditional lower atmosphere temperature measurement. The second thing is, this is the one that gives us the magnetic field strength, but this gives us the wind. So we basically measure the same thing, just look at the shift, we get the winds out. So in addition to the magnetic fields, we can get, we also obtain line of sight winds. We haven't made an attempt to get different altitude winds yet, but we can get a temperature profile every second from the 4 beam of measurement along the track. So basically we have an image 4 track of this high spatial sampling measurements of the winds and temperature in a region, temperature between 45 to 85 kilometers. And this is very, very good data product because we have 1 second measurements, everything. Preliminary estimate that for the temperature, you can see 40 kilometers, we have excellent measurement. You know, it's about temperature, 1K precision or so. We can actually see the gravity wave perturbation, even although 40 kilometers slower, but high altitude, we can actually see. You can see the bore changes, vertical wind changes and all that. So a lot of products are there for the community to use. We're looking forward to this product so we can share with you. So I don't want to go back to the measurement summary again, but I do want to say a few words about the launch date when we're expecting. We are working with the launch vehicle folks. We're expecting to launch 2024, late 2024, early 2025. And the data, we are working very hard. After the 2-month checkout, we are going to release the data to the community to use. For now, we really would like to share with you is the one we are open to work with the community. But I would like to tell you about the product and what you would like to use so you can plan your research or you want to understand more, work with us. We have all sorts of capabilities. We can do cross-track flying. We can have 2 cross-track, 1 along track. So a lot of things that we can manage how we get the data and then coincident measurements or all that. So please work with us. And we have a workshop coming up September 18th to September 19th is an open workshop, both virtual and on-site, and registration open. So website, just easy.jhu.apl.edu. I'll leave this last slide open. So if you're interested, there are 2 papers, main 2 papers quoted in here. One is using the MLS data to demonstrate the technique. The second one is the technique itself. So, thank you. Any questions? Oh, yeah.
Okay, so thank you very much. This is Shen Zhang from MIT Haystack. So I was wondering if you can address the vertical velocities. Can you measure vertical velocity as well, in addition to horizontal ones?
Actually, we are, if you can imagine, we actually measured the vertical because we have 4 channels. 1 channel is nadir looking. Because we had to get the reference. 1 channel is nadir looking. So the first nadir channel, if we know the oscillator, we call it local oscillator frequency well enough, is we can monitor the vertical velocity movement as well. The rest of it, we have vertical as well as cross track. And with certain satellite, we plan to tip the angle a little bit so we can get wind vector rather than just the cross track winds. Good question. Thank you.
Yeah. Hi, Sam. This is Xinzhao Chu from CU Boulder.
Yes.
First, thank you for a very nice talk. Not only the contents are exciting, but also your enthusiasm and the passion in the talk were very, I should say, contagious, right? Yeah. Okay. So I have 2 questions. The first one is this Zeeman effect is a really good idea, but when you talk about that, you said the splitting is proportional to the magnetic field. This is on the first order of approximation.
Yes.
You know, there's always non-linearity there.
Right.
There's a dependence on the square of magnetic field or something.
Yes.
If you only measure the total magnetic field, that is, you probably can ignore that. It's okay. But you are trying to measure delta B, you know, the disturbance of magnetic field caused by an actual jet. So have you done error analysis, the non-linearity caused by the total magnetic field versus this delta B caused by actual jet?
That's an excellent.
Yeah, that's my first question.
Yes.
Second question is about this secondary product. You try to get temperature wind.
Yeah.
This is a really brilliant idea. But I want to know, you know, say when you get to 500 kilometers, there's insufficient cohesion. Do you get these kind of really the temperature or wind representing the surroundings, or only the oxygen itself?
We are remotely measured. So our measurements independent of satellite altitude. The higher altitude, just spatial resolution increase because emission, the contribution function coming from 80 kilometers. So, so regardless of where you make the measurement, emission absorption feature happen down low. Currents right here, signals right here. So we are remotely measure the winds. So we are just like air glow measurements, peak around 80 kilometers, roughly about a Gaussian layer, just like you have a Manel band instruments on board. But we can do both day and nights.
But then the measurements representing 80 kilometer wind,
Yes,
not 500.
that's right. Not 100% at
Oh,
all.
okay,
It's
okay,
remote.
okay.
It's
Yeah,
remote.
yeah, okay.
Okay.
How about
Yeah,
my
get back to
first
your
question?
first question. I did look into that, into the higher order. The higher order term depends on, of course, you know, if you want to say we derive 1 nanotesla out of the 65,000 nanotesla, so what the coefficient of that? One probably error bars is smaller. This higher order term might affect the one accuracy of the 1 nanotesla. Okay, then for accuracy, when we talk about measurement capability, we look at two things. We look at precision as well as the accuracy. All right. So in terms of precision, we are looking at the structure changes. We are not looking at whether the magnetic field is current induced 701 nanotesla versus 699 nanotesla. No, we are looking at the bulk variability of the structure. So if you have any nonlinearity of changes in here, probably smooth out by the structure variabilities. So that's the answer. We are not going after the accuracy of the measurement to 1 nanotesla. No, we are measuring the relative change of the structure caused by.
But you still have this the real perturbation caused by actual jet versus
Just
you
to
know, the
quickly
change of
interject.
the-
We do have some questions online. Is it okay if like you follow up later with that? If that's okay, just to like, yeah, okay, yeah, just because like other people have questions and I don't want to just be one. And we are running out of time. Yeah, so let's just answer the first side of question there. Dr. Yi, what's the advantage of using Zeeman effect instead of in situ measurements?
So what kind of job opportunities for? Oh, I'm sorry. I was surprised by that.
You can answer that one too if you want.
Okay, like I think I hope I explained well enough. Yes, indeed, you can make in situ measurements. In situ measurement, you can fly something through the electric jets. You can get very nice profiling. But this is a systematic measurements imaging. But if you put further away onto the satellite, which you heard about it already, decades of measurement, but a few hundred kilometers above the electric jet, then you put a magnetometer on board in here. 400 kilometers, your spatial resolution is about, I would say about 1,000 kilometer type of space. You basically, the smaller structure gets smeared out. And the other thing is by using the remote sensing, we have 4-channel imaging that's equal to 4 satellite fly magnetometer on different plane. So in other words, also cost saving. You develop imagers, you can save a lot of money, can image magnetic field structure from single satellite. So this is just the beginning of the Zeeman technique because we have 4 smaller ones. We can find, but we can put in more sensors on. All right. Any other questions?
There is another question, but we are 15 minutes late. So we should probably close the plenary session, but thank you all to our speakers and thank you all very much.